Good morning, everyone. So this presentation deals with the ORV3 power shelf and power supply development. It's an update, so it's actually everything what happened between the introduction of the project during the Global Summit this May and today. So the presentation, as Hamid mentioned, so the presentation is a joint effort among 3 companies. So my name is Ralf Pieper. I'm the R&D director of Delta Energy Systems located in Germany.
Hi there, my name is Harry Soin from Artisan Embedded Power, a division of Advanced Energy. I'm responsible for the hyperscale space and located in San Jose, California.
And my name is Lam Vu. I'm Director of Engineering for Light-On Technologies, and I'm based in Plano, Texas.
Okay, so on this page, you see the today's content. So the first part will be introduced by myself. So it will be a short refresh on the ORV3 spec. Then I show you the efficiency achievements, what we had on our first prototypes. And I will also show some details about the current sharing and regulation of the unit in the shelf. And I will also show a GUI, so which you can run on the PC to check all these readings from the power supplies. Then in the second part, this is presented by Harry. So he will introduce the ITIC compliance, so input transients, write through, then total harmonic distortion, power factor, also efficiency of the artisan units, as well as some airflow and acoustic measurements and achievements. And the last part will be presented by Lam. So he will show some output transients of the power supply and shelf. So during load transients, during startup in the shelf, he will talk about the output voltage startup timing and programmable rise time. And he will also show some protections of the constant power mode when the units will drive into overcurrent. Okay, so let's start with the short refresh of the spec. So first of all, the rectifier. So the input voltage range is high line, so it's 180 volt up to 305. So 240 nominal and 277 volt nominal. The output power is 3000 watt. The output voltage, if the unit is applied with AC, is fixed 50 volt. And if the unit or the rack is running on the BBU, the bus voltage will be 48 volt. Output current is 60 amps. The hold up time during AC loss is 20 milliseconds. The peak efficiency will be 97.5% and 96.5% at full load. For current share, we will have active adjustment plus a Droop share. Communication, the power supplies have I2C communication to the PMC and Modbus. So in the moment, we have implemented both. The size is 73 millimeter wide, 40 millimeter high. So this is 1 RU and 520 millimeter length. And here you see the shelf, the 1 OU shelf. So this has 6 slots for the power supply. Oops, it's a little too slow with the pointer, sorry. So it's the 6 power supplies on the right side, and on the left, there is a slot for the PMC. The total installed power is 18 kilowatt, but it's a N+1 redundancy. So the 15 kilowatt it's a 5 power supplies. This is usable. Again, 50 volt fixed at AC and 48 volt at BBU. So it's 300 amps output current. It's 6 times or 5 times 60 is 300. And the output connector, as Tiffany mentioned, is the Amphenol bar clip 500 amp BK500. And the communication at the end will be Ethernet via the PMC module. And the size, it's the 21-inch wide, a 1 OU, 48 millimeter high, and 713 millimeter deep. So some words about the motivation for this V3. So I do here a comparison with the V2. So as you heard, the peak efficiency will be 97.5 at around 50% load. So this means we have 2.5% losses at around 1,500 watt, which results into 38 watt. And for full load, we have a 96.5%, which is 3.5% losses at 3,000 watt, which results into 105 watt power dissipation. In comparison to this, we have the V2 with the 12 volt output, which has a titanium efficiency, but even increased full load efficiency. So the titanium calls out for 91% at full load. And here this unit already achieved 94%. But still, if you calculate the losses, we have 60 watt at half load and 180 watt at full load. And if you compare these two numbers, so we have approximately 40% saving for the V3. And this is not all, this is just the power supply. So also for the distribution, we can save energy because we have the higher voltage and lower current. So on this slide, you see the efficiency measurement, the details. So the yellow curve is a 240 volt input and the blue one is 277 volt. So this is everything including the fan. And you see around 1,400 watts, so around 50%. We achieved this 97.1 or even 97.59 peak efficiency. And at the full load side, for 277, we are above this 96.5. So for 240 volt, we are still working on improvement, but we are on a good way to also achieve this 96.5. This page shows the current share. So this is between two units with 6,000 watt loading. So the red curve is the spec. So we have 5% until 85% load and then 3%. And if you see here at 5% load on the left side, we achieve 3.9% current share, and at full load, we achieve 1.77%. So, and the curves are very linear, so very stable. This page shows the regulation, so the Droop curve. Here I have to mention it's before the spec change. So the latest spec is 1 volt, as Hamid mentioned before. So this measurement was taken for different input voltages and frequencies. But here even you see they are all laying on top of each other. So we have just one straight line. And this was plus minus 250 millivolt. And the new spec, so it's an adjustable Droop between 1 and 5%. And the default one is 2%, which equals to 1 volt. So at zero load, it will be 51 volt. And at full load, it will be 50 volt. But everything is adjustable by firmware. Okay, so the last pages, this deals with the PMC and the GUI. So we are working in 2 steps. So the first step is the connection to the PC via a COM controller. So we call this a PMC Lite. So the PMC Lite, this collects all the information from the power supplies via PM bus, via I2C. And then the controller talks via I2C or RS485 to a communication box, and this translates the data to the USB, and you can connect the PC to check all the values. And the second step will be the PMC with OpenBMC, which has an Ethernet port. So then you can directly connect the shelf to the switch, and you get all the data via Ethernet. And here is one snapshot of a GUI reading. So here we see an example of 12 power supplies running in the 2OU shelf. We see, for example, input voltage, input current, input power, output voltage, output current, output power, and some temperatures, as well as fan speed and the status word of the PM bus. So you can get all the details on a glance if you look at the GUI and you see the current sharing and everything. Okay, so that was my part. So for more information on the prototypes, you can connect or contact me directly via email. And yeah, as you know, we have the 1U shelf, the 2U shelf, as well as the 3 kilowatt power supply and the 5 kilowatt power supply. And then I hand over to Harry.
Thank you. Thank you, Ralph. My name is Harry Soin from Artisan. So here at Artisan, we have developed 1OU and 2OU versions of the power shelf, and the rectifier is 3 to 5 kilowatts. And I'm very excited to provide you an update on the development status of these and share the test results with you all. Next slide, please. Thanks. Perfect. So my agenda includes providing an update on the key aspects of the key parameters, including power factor, THD, efficiency, talk a bit about the ITIC, and finally, the airflow and the acoustics. So first of all, let's dive into ITIC. ITIC essentially is the Information Technology Industry Council. So this agency has outlined the AC voltage boundaries for the IT equipment to ensure the compliance, and they are able to ride out the normal day-to-day disturbances. So there are three key aspects to this, and they are like a dropout as well as the sags. So this slide here demonstrates that those three parts, which are when the voltage first drops out from 200 volts, which is considered nominal in this case, down to 0 volts, and it's supposed to stay there for 20 milliseconds. The second part of this design is when the voltage goes down to 140 volts, and it has to stay there for 500 milliseconds. And finally, it's from 200 down to 160 volts and stay there for 10 seconds. So again, as you can see, they are tough, stringent requirements. So all in all, as you can see, the 48 volt line stays stable. These are the test results from the actual units, and the power supply is able to sustain this without any issue. Moving on to the next slide. So the other part of the ITIC requirement is a sequential drop, which is quite a bit stringent. In this case, the voltage drops from 200 volts down to 0 volts initially. As you see on the left-hand side of your screen, it stays there for 20 milliseconds. Then it rides up to 140 volts, stays there for 500 milliseconds, comes up to 160 volts, stays there for 10 seconds before ending up at 200 volts AC. And as you see from the top curve, the 48 volts remain stable. So the unit is supposed to meet these challenging requirements without any issue. Moving on to the summary slide, I wanted to share this summary slide with you so we can all see, where I'm going with this. On the picture on the right shows you the sequential drop that we talked about in the second slide, where the voltage goes down to initially 0 volts, stays there for 20 milliseconds, comes up to 140 volts, comes up to 160 volts, and before coming to full power. And then on the left, you see the three individual test conditions. So all in all, so there are stringent sag conditions and dropouts that unit needs to endure with. So the point of the matter here is if the application does not require this severe level of drops and disturbances, one can design a power supply which will have a better power density and perhaps lower cost. So just to show you where I'm going with this next slide. Thank you, Ralph. So this slide here shows you the PSU design considerations that one can take into account. So, when we talk about the surge, the sags, which was going down to 140 and 160 volts, that causes stress on the PFC front stage, typically the inductor, right? Because it has to endure, it has to have a higher margin to avoid saturation. The PFC FETs and the diodes have to endure higher peak currents and hence higher stresses. For the dropout condition, we need a much higher hold-up capacitor. And these things take space. So if you look at the bottom table, and what essentially it's telling me is that if my application does not require that severe level of compliance, I can cut down my hold-up capacitor. I can probably size my inductor and FETs in a proper fashion so that I can get at least here in this picture 4 drops of 4 watts per inch cube improvement in power density. Thanks, Ralph. So that was the takeaway from that slide. So now moving on to sharing the measurements with THD and power factor. So as you see on the right hand side, we are able to comply with power factor in most conditions. Some work needs to be done at lower loads, and that's always a tricky part. And especially as you see on the left, ITHD, we are getting there. We are doing some work. We are doing the firmware optimization so that we can minimize the distortion. And during the next update, we want to share the results which are compliant. Thanks, Ralph. So one of the key important part of this design, which I'm really glad to share with you, is the efficiency. So here you see the 2 curves. The top, the curve in the orange color is the 277 volt operation. And the 277 volt operation, we see we not only meet the peak efficiency, we are also above the minimum required efficiency. At 240 volts, which is the blue line, there is slight amount of work that needs to be done to get to the peak efficiency, although we are compliant with the minimum efficiency. So one thing I want to point out to you is if you see the design, the topologies we have deployed in this scheme, our efficiency range is quite flat from 30% to 90% of the load, so that you can get good savings, which Ralph pointed out earlier. So we want to maximize the savings in terms of efficiency, in terms of the operating cost. Thank you. So just putting things in perspective and looking at the packaging density and the hold up trade-offs. So the key essence here is if you are able to take all those considerations into account, one can reduce the size of the PSU. If you have stay with the lower hold up time, increase the power density, perhaps have a slight gain in efficiency as well. So that was just a takeaway from that slide. Thank you. So moving on to the last section where we will be talking about the shelf impedance and the acoustics, which are often ignored. And again, my talk won't be complete if I don't touch up on the interop. So from the interop perspective, here we will be looking at the rectifier itself. And we treat rectifier as a fan. The curve in red is a PSU PQ curve, which is a measured airflow in the system and the airflow that rectifier is supposed to have in terms of its performance. So one must specify the minimum and maximum values of this curve so that if the airflow is not enough, then the rectifier could have challenges, or rectifier may not be able to work in a shelf which has a higher impedance. So one needs to specify the PSU PQ curve as a part of interop. Thanks, Ralph. And the next 2 slides, which you're going to be looking at, is the PSU shelf impedance. Again, from an interop perspective, this really is a key parameter. So PSU shelf impedance is the back pressure or the resistance that the rectifier would see in general. So this slide here shows the measured shelf impedance for a total of 6 rectifiers. So one must specify the minimum and maximum values you see in these 2 slides, because in order to facilitate interop between the vendors, the PSU has to work in the other shelf and vice versa, so that we can get the optimum performance in both of these conditions. Just moving on to the last section of acoustic noise. This part has legal as well as the human aspects, always, which need to be factored into the design, because the noise by itself is, this is what it is. It's the noise, the audible noise. So the spec for acoustic is 85 dBA, which isn't part of our spec. So what we are showing here is a technique or a procedure where we have measured a single unit, and the sound pressure, or the dBA in this case, was 66 dBA. And we are providing a logarithmic method so that one can calculate without, in fact, putting 6 rectifiers or 12 rectifiers in the shelf to come up to a number as to what will be the expected noise level. So if you look at this picture, as it shows up that we will have about 77 dBA of sound pressure, which is well within the spec. I just want to caution one thing: it does not take into account the rack effects. The rack could sometimes provide damping effects, which can probably bring down this number, or it can provide resonance as well, which could increase these numbers. So the final number could only be validated once we come to the proper measurement. And finally, my final slide here, I would like to showcase and share with you the things we have designed at Artisan. We have a 1 OU power shelf, shows you the front and the back view, the 2 OU power shelf. We have designed 3 to 5 kilowatt rectifiers and the controllers, which Hamid mentioned earlier. And please feel free to contact me if you need more samples or any details regarding these offerings. Thank you, Ralph, and I'll hand it over to Lam, who's going to walk you through the light-on version of this design.
Hi, my name is Lam Vu from Lydon. I just want to show some of the feature of the power supply that relate to customer and how you use the power supply. And one of the features is programmable rise time. And this is important in startup so that the power shell can handle the amount of capacitor external, that connect to all the server. And the power supply can have a programmable rise time going through the communication through the PMC. And here I'm showing through different rise time at 50 millisecond rise time, at 200 millisecond rise time, and 400 millisecond rise time. And these rise time can be stored in the EEPROM so that once you program it, it will remember. Okay. And this is the power shell start up through the sync start. And you can see that, this is in a 6 power supply in a 1U shell. And you can see that they all started together, and the load is almost full load here. At 100 amp per division, you can see all 6 power supplies start together. Next slide, please. Yeah. And this is the transient response in the shell. This is in the 1U shell. So you can see that the step load from nearly no load to more than half load, and up and down. The deviations is about 1 volt. Okay. And this is the transient response from half load to full load. And the full load is a 300 amp. And you can see that the ripple is less than 1 volt. And okay, the can you go back one slide, Ralph? And the extra ripple you see here is the ripple from the PFC bus at when you have a step load, and then the PFC will catch up and then it smooth out. Next slide, please, Ralph. And this is also show a bigger step load from nearly from like 5% load to like 90% load. So you can see that the power shell can handle it, and the transient response during this time will make sure that all the power supply operate within the limit, and there will be no shutdown even during a large step load, up or down. And in overload, the power supply, the specification is that the power supply will do fallback when there is 105% overload, and it will maintain that voltage so that the rack will have time to make the correction in the load in order for the system to recover instead of shut down. And you can see that this is test with 3 power supply. So it's a mixture of load, constant current load and some resistive load. And you can see that when the current go above the 105% limit, then the voltage will fall back, and it will hold at that level. And until the current goes above 120%, then the output voltage drop below 44 volt, and then the power supply will shut down. And you can see that it's another time we do the same overload, and then let the load recover to below full load. Then the whole system will recover without any overshoot. And that's the information of some of the performance of the power supply in the shell. Now it's time for us to answer if there is any questions to any 3 of us.
Yep, thank you for the presentation. It was great to see you guys on 3 different companies. They work together and share this information. Yeah, we have around 10 minutes left for questions, so that's great. Let me go through the questions to see, share the questions for you. Question from Brian: have either of the presenters evaluated the impact of this new design on line voltage and current power factor? Sure, they pass IEC 61000-3-2 on an individual unit basis, but when you scale and put hundreds and thousands of these on a circuit, the collective THD of voltage and current can be poor and cause instability.
If I may answer that, Hamid, as you saw, we talked about the THD as well as power factor work, and 61003-2 is indeed defines all the different levels of harmonics in the specifications. And the good news is it's sort of a logarithmic method, and I think we are on a good path. The real challenge one faces is the 3rd and the 5th harmonic, and once you get hold of that, I think we have a very good path to meet the 61003-2, and I think we're in a good way, and we should be able to show better results next time during the next update. I don't know, Ralph and Lam, you have anything to add to that?
No, I'm actually agreeing. Yeah, you're right. Yeah.
So that's basically, maybe the simple way to ask the question is that if each PSU meets the IEC 61000, then we have several of these modules. Do they have a limited amount of THD, or there's another term we need to also take into account?
There is no real specification around it. I think, Hamid, that's a very good question. And the only thing working in our favor is it's a logarithmic method. So the contribution when you do a collective will probably won't be that significant.
Mm-hmm.
But we need to pay attention to the individual unit's performance to meet this well.
Maybe I start with individual, but doesn't end
Yeah.
there.
Okay. No, it doesn't end there. Yeah.
All right. There was one comment from Jeff Arthur. He's saying that we are finalizing new power supply measurement data formats for Redfish support, which would be included in OpenBMC, asking the power supply expert to please review the documentation. No Redfish experience needed. See the PDF. So that's on the comment. I think they are doing a great support to bring Redfish to the community and power system. Please, everyone, please support and add the requirements. I think as part of the PMC we have to do so. I encourage others also to support them as well. Yeah, would you like to see the management support? Yeah, he's also asking, he wants to align with Ethernet and management best. Yes, sure, Arthur and Jeff Arthur, we would do that. One other question is that, is talking on ITIC requirements that you guys mentioned. Is this a requirement? Is this ITIC requirement an industry-wide requirement, or like few companies adopt this? Do we need to design for this one for all our systems? How is your perspective on this ITIC requirement?
Well, I can state that from the artisan's perspective that, I think this is really key that, that we should take the application into account before going all out. And as you all saw, right, if you're using a large electrolytic capacitor, 20 millisecond or whatever, it has an impact. It stresses cooling, it has, limited airflow, and all the other factors go along with it. So to make the long story short, I think we should do this application specific and not just blindly follow this ITIC requirement.
Okay. So we need, the application need to know if they really need it.
They're correct.
Seems like it's a significant, there is a significant resource requirement to make this one happen inside the PSU.
Absolutely.
Yeah.
I mean,
because with ITIC, during the 70% drop, we still have to support full load. So the design had to have a lot of margin in order to handle that. So that does add to the cost and to the complexity of the unit.
Yeah. So just to say, that's a very good feedback. I think the feedback is coming back to me. Thank you. Yeah, I think, I heard about this one as before. That's a lot of complexity to meet ITIC. Yeah, it doesn't have to be on the, as a hard requirement on a spec. I agree with you, because not everyone wants it. So we will revisit this item for sure. Just one item, which piece of the ITIC is most difficult? Is it the 2 millisecond write time, write through, or is it a dropout at different range, higher voltage? Which piece is the most difficult, or is it like all of them is difficult to achieve?
Good question. I think it's a combination of all three, right? Because one leads, like the SAG 140 and 160 leads to over designing your PFC and your power factor components, and the other one results in hold up, right? So I think one needs to compromise between all three.
Okay.
I think we talked about limiting the hold up to 15 milliseconds, right?
Yeah, I think recently, we discussed, maybe we can limit it to 15 milliseconds to make the system work better. So we probably need to update the spec to 15 to meet the 15 millisecond. To my understanding, there is no hard requirement for the hold up time. At least we want to meet one cycle, which is around 15 milliseconds. I have seen PSUs even with 10 milliseconds.
Mm-hmm.
Yeah. Seems like we may land at 15 milliseconds and have to revisit the ITIC. Yeah, I see on the comments, somebody says it's a ITIC is data center requirement. It seems it's not for everybody. Some companies,
Correct.
they do, some companies, they don't.
It's an old CBA curve, right? It's Information Technology Industry Council, so which does not really apply to all, data centers.
Yes. Okay. Let's see. I don't see any new questions that you guys have to answer. Several people, thank you you all for the great presentations, and
Welcome.
I think they will catch up with you later for more details, questions, and other things.
Mm-hmm.
I was going to say maybe Lamp. There was one question in the chat in the Zoom meeting here that others may not have seen. Maybe if you want to restate that question in your answer as well, just before we hand over to the next presentation.
You're asking, I don't see the question. So.
Let me read it for you. Are you designing PSUs with 20 millisecond AC dropout right through per ITIC?
Yes, we do design for 20 millisecond right through. So actually, in order to have 20 millisecond right through, you have to have at least like 22. So that give time to detect that the line coming back, and then time for the PFC to ramp up to support full load again. So 20 actually, in more than 20 in order to have 20 millisecond right through.
All right. I think that was the item we said we can maybe relax the spec, maybe bring it down to 15 millisecond and 15, and maybe revisit the ITIC requirements. So we will work on that and get back to you. I think we are almost out of time.
Okay.
Done with presentation.
Thank you very much.
Yeah, thank you much, Ralph and Harry and Lam for great presentation, and looking forward for great contribution.
Okay.